enjoy the beautiful weather, which I didn't expect to have this time of the year. I'd like also to thank the organizers for this invitation, the opportunity to be here. What I'm going to talk about is, and this is something which has to do with the standard cosmological model. As you know, about 25 years ago, there was a major breakthrough in our understanding of fundamental physics, and in particular gravity. It was realized that gravity, in fact, is a repulsive force on cosmological scales, and this repulsive nature was modeled in various ways, but the simplest way to it was modeled was by incorporating in the Einstein's equation the cosmological constant. So in this way, we constructed the so-called standard lambda CDM cosmological model, which is based on the assumption that the energy of the universe, by about 70%, consists of dark energy, in particular by the form of the cosmological constant, and the rest, 30% approximately, is due to a fluid which has the properties of matter, which is of dark matter and regular matter. Now, for about almost 20 years, this model was tested repeatedly by a wide range of cosmological observations. It was realized that, in fact, it has an excellent fit with the data, and that's why other more complicated forms that were tried did not really manage to somehow survive, and it remained, and until today remains, the standard model of cosmology. However, during the last, let's say, 5 years, there have been some indications that we may be approaching the era of perhaps realizing that a new understanding of fundamental physics is required to understand all the cosmological data, and this is due to the so-called tensions of lambda CDM. Tensions of lambda CDM are in fact various measurements of fundamental parameters of the model, like the Hubble constant, which are in conflict with each other using different methods by up to 5 sigma and beyond. And these measurements, these conflicts in these measurements, which appear to be due to the requirement of new degrees of freedom and not due to experimental errors or journal errors, because in fact they have been consistently being there for at least 5 years. Meanwhile, therefore, the introduction of new physical degrees of freedom in the theory, which will make this theory fully consistent with these conflicting results for the parameters. So new degrees of freedom means a different model. So in this talk, I will try to describe these conflicts of measurements about coming from the fundamental parameters of the models, and then discuss possible methods, possible models that will induce new degrees of freedom in the theory, such that it will become consistent with this tension, these conflicting measurements of fundamental parameters. Now let me start with pointing out the structure of this talk. I will first review the standard cosmological model, which is the lambda CDM model. Then I will describe briefly the 3 main classes of tensions, which during the last few years have been introduced. These include the Hubble tension, the growth of perturbations tension, and the dipoles cosmological tension, which tries to somehow question the validity of the cosmological principle. Then I will discuss, I'll focus on one of these tensions, which is according to most cosmologists, the most prominent one, and this is the Hubble tension. And I will discuss in some detail some methods that are used to measure the Hubble parameters, and then thus I will try to indicate the foundations from which this tension emerges. Finally, I will discuss some of the basic classes of models that have been proposed to resolve this tension by introducing new parameters in these new physical degrees of freedom in the standard models, and we will see to which level are these models successful so far. I will also discuss a particular approach which is my personal favorite, which involves a gravitational transition event at late times, which could in fact lead to a resolution of at least one or two of these tensions. Now, let me briefly remind you the standard cosmological standard model of cosmology, which is the ΛCDM. It is the cornerstone of the model, of course, is the cosmological principle, the FRW metric, which you see there. You have the scale factor A of T, allows for a calibrator K. And the first ingredient is cosmological principle. The second ingredient is general relativity, which through this metric leads to the Friedmann equations, which is, of course, we have this standard equation for the Hubble expansion rate as a function of time. And the Relativity equation, the iteration equation, which indicates that a cosmological constant, if it's positive, can indeed induce accelerated expansion. And in fact, that was observed on the cosmological scale. So that's why one introduced initially the cosmological constant, but it turned out to actually fit very well the plethora of cosmological data, not only with the accelerating expansion. So that's why this is the standard model, not only because it induces acceleration. And finally, the Bianchi identity, which is the oscillation of the energy momentum tensor, and you have this fluid equation here, which indicates that if we want a constant density, then you have to have an equation of state which is rho equals minus p. And so this part of the cosmological constant corresponds to a equation of state of if it is in a gravitational fluid, it corresponds to which is constant in time, its density corresponds to the equation of state which is minus 1. So, for example, for matter where the pressure is 0, we will get this evolution with the scale factor here. Now, the energy components that one can, we know that exist today and have been measured are these: the radiation, which is scale of 8 to minus 4, the matter. The calibrature part is, in fact, very close to 0, so we usually ignore this. It has been shown by the CMB measurements. And of course, the cosmological constant part, which is the omega, is the ratio of the density over the critical density at the present time. We find it this way, and this is the critical density as you see here. Now, usually, this equation is expressed through measurable quantities because to measure the scale factor at a given time in the universe, we have to know we have to measure actually the redshift, which is connected with the scale factor at the time of emission of the radiation, and we have this relation between the redshift and the scale factor. So by substituting here the scale factor by 1 plus z to the minus 1, we found this standard equation, which is this central equation of the standard model, which tells us that the ingredients of the universe as we know it today, at least at the background level without perturbations, include the matter, radiation, which is very small today because the redshift is much faster, and of course this part, which is the part of the cosmological constant. So this is the background equation that defines the standard ΛCDM model, and we have, of course, 0 gravity. In addition, of course, we have perturbations and some other parameters which have to be included, but this is the central equation. So the equation is what are the values of this parameter? You see it has some parameters, has omega 0 matter as a parameter, and also have the Hubble constant as a parameter. And these parameters at least have to be measured very well and lead to values which are in fact consistent among different measurements. Now this happens for omega 0 matter, these are more or less consistent, different measures of omega 0 matter, but H naught, in fact they are not. So even though this part, which we usually call E of Z, the same of the Hubble expansion rate with the redshift, appears to be more or less consistent and well accepted by most observations. This part here, H0, is in fact in very great debate what is its correct value. In fact, the difference among different very high quality measurements is at least 5 sigma, and this has persisted during the last at least 5 years. In fact, it's been getting worse. So what's happening here? What is additional ingredient needed to reconcile this issue. And here you see the various measurements of the Hubble constant, which show the Hubble tension. The most precise measurements, but not necessarily accurate, are coming from the Planck CMB measurement, the CMB spectrum. Under the assumption of this ΛCDM expansion rate, one obtains this value for the Hubble constant, which is you see around here. This value. If one can try to measure H0 using the so-called distance ladder approach, which directly measures locally the Hubble constant, one obtains the most accurate measurement of this one, but you see there are different measurements here, which are not so fully constraining, but they tell you the direction. And these are the corresponding data points. These are the early, so-called early time measurements based on the CMB mostly, causing one to around. And these are the so-called late time measurements, which are based either on the cosmic distance ladder, direct measurement, or with other local late time methods. As you see, these are the two bars. This is the most accurate measurement of H0 using distance ladder, the so-called SUS measurement by the team of Ioannina collaborators. And this is the CMB measurement in this band, obtained from the Planck CMB spectrum. And you see there is a big disagreement between the two, but of course the other measurements, many of the other measurements which are late time, seem to have very big uncertainties, and perhaps be considered with work. But it's these tensions which are traditionally getting stronger as time goes by. So the RIS 21 measurement, the SUS measurement, shows this value 73.04 plus or minus 1.04. And the corresponding CMB measurement from Planck is 67.36 plus or minus 0.54. And these two numbers are in disagreement by 5 sigma, which seems to increase also with time. Previously it was less. This is the latest measurement, which in fact is 5 sigma. So this is the Hubble tension. And the question is, of course, what is the degree of freedom that is hiding and we're probably missing if this tension is in fact real? Because, of course, one cannot exclude fully the possibility of some unknown systematic which prohibits these two, which invalidates the two measures. So, what is the difference that distinguishes these two classes of models? What is the different assumptions? Some of these assumptions must be wrong. So, what's the assumption that is wrong here? Which will indicate the correct, the missing degree of freedom. And so this is really this, in our recent review, which reviews all these challenges, including this one as the main one, and shows all these challenges of ΛCDM in a concise manner, so I'm going to go through some more details about these issues. One can make this mistake. So the second tension is the so-called growth tension. It's a weaker, it's not 5 sigma tension. It's about 2 to 3 sigma, but it also has been persisting during the last 5 or more years, or 10 years. And this actually is a tension among these two, with these two parameters, the sigma 8 and omega 0 matter tension, which sigma 8 is the RMS density fluctuations cosmologically on scales of 8 megaparsecs, and is proportional to the initial amplitude of the primordial fluctuations. And this is omega 0 matter, which is in this case is seen as a driving force for fluctuation growth for the growth. So it looks like these two parameters can be measured mostly as in a combination, this is called SA combination, which is the product of sigma 8, the primordial amplitude fluctuation to the 1, times the omega 0 matter to the 1/2. And this product here, which is measured quite accurately, you see is elongated along this hyperbola somehow, this plot here, indicates the strength of the growth of cosmological perturbations. Because the bigger amplitude we have, the more perturbations we have at late times, and the bigger omega 0 matter, we have also the stronger the growth, because omega 0 matter is the driving force, if you want, for the growth. It's like it amplifies the growth of fluctuations. So this one way to measure this parameter is using these so-called redshift space distortions, which measure effectively the galactic peculiar velocities of galaxies at late times at various redshifts. And you see that there is this is the late time observations, and this is the observations from Planck, which are obtained here, assuming this measures the primordial essentially amplitude, and assuming general relativity, one obtains this contour scale from the CMB, which appears to be some conflict with the measured values. And you see that SA appears to be lower than one would assume would obtain using the CMB measurements assuming general relativity. A similar plot is obtained with weak lensing, which also measures the distortion of galactic shapes due to foreground structure, and can also measure these same parameters. You see that here this hyperbola here along this is also obtained for constant sigma x, so you see this, that's why it has this shape here. And these are the black values, and you see here that they are above this hyperbola, which means that in fact we measure locally weaker growth than expected from the early time measurements plus general relativity. And the same is obtained by using cluster counts measurement, measuring number of clusters at late races, and comparing with what we would expect from the general relativity plus the primordial plus the CMB measurements. And you see we have the same phenomenon here. This hyperbola here is below the measurements of class. So these distinct classes of measurements all seem to indicate that there is weaker growth of fluctuations, but not by very significant in this case amount, about 2 to 3 sigma, compared to the expected values of growth from relativity and time measurement. So this is the second set of tensions. The third set of tensions is the so-called cosmic dipoles. The cornerstone of such a model is the cosmological principle. So, in the context of this principle, one would expect that beyond 100 megaparsecs, one should start seeing homogeneous and isotropic, of course, universe. Now, there are consistent measurements which indicate that this may not be true. Maybe this anisotropy that we see in the sky from various measurements appears to be much stronger and more persistent than expected in the context of the standard model of cosmological principle. Here, for example, you see a paper, a result from a paper which measures the bulk flows of galaxies using this survey which is called Cosmic Flows 4. And this survey measures distances to galaxies using various relations, coefficient relations, etc. And also measures redshifts and compares to the Hubble flow, and therefore finds peculiar velocities of galaxies with respect to the Hubble flow, and then using these peculiar velocities, one constructs the velocity field on large scales, and they find that on various scales, for example, if we average over 100 megaparsecs, we have these components of velocity that they find the bulk flow in this direction, this component, and this demand of the velocity. So they find bulk flows which seem to be, in fact, increasing with the scale of the volume probe. While the standard model here, this is the red line, would predict that this would decay with scale. The bigger the scale you take the average velocity, the smaller the bulk flow should be. Now these people find the opposite. Not only they find it to be bigger than the prediction of ΛCDM, they also find it to be increasing with scale as opposed to decreasing. So this is a paper that has attracted, this is a consistent measurement, they also have previous measurements of that, and also other groups measure the same thing. This is not a single group which does that. Of course, this is the most advanced group, but of course other groups which measure the similar things are consistent with this result. So the question is, what is the thing that actually induces this anisotropy, this persistent anisotropy in bulk flows on these scales? In addition, there have been some studies which try to measure the density of quasars at redshifts of about 1 or bigger, which means that bigger distances than this one, about up to 700 megaparsecs. And because we are moving, of course, with respect to the CMB frame, we expect to see some anisotropy in the distribution of quasars. And this anisotropy we expect to see because of aberration and because of Doppler selection effects. Is this one here? This close here. This is the expected anisotropy, this is the dipole anisotropy we would expect to see due to our motion with respect to to the homogeneous tropic CMB frame. What we actually observe is this. What is the equation that we use? And you see that there is 5 sigma difference between the two measurements. So why are the equations so much more anisotropic than expected by our velocity with respect to the CMB frame? The direction of this anisotropy is consistent with the CMB velocity direction, and you see here that it's very clear. This is the CMB velocity, and this is the 1 sigma region of the anisotropy direction. So this is a second hint, and this in fact has also been verified using dipole galaxies, total equations, where the magnitude for this is also much bigger than expected by the CMB. These are two surveys of radio galaxies, which are also very far away. And you see that in fact also the disagreement with the CMB is significant, even though the two surveys are not fully consistent with each other. So there may be some issues in this part of the analysis in the sense that they are not fully consistent with each other, because they are not consistent in fact. So we have a large amount of tensions recently in the ΛCDM, and the question is, of course, if we have such big tensions, why is this still our standard model? Here are the directions of the flows. You see that this is the Q dipole, this is the radio galaxy dipole, and this is the back flows, and this is the CMB dipole. See, they are all very close to each other here, and so there is some consistency in the direction. So the question therefore is, why is still ΛCDM our standard model despite all these tensions? And of course, the first reason is inertia, where it has so many successes with respect to other observations. So despite of this very many sigma tensions, it's hard to abandon a model which is so successful in the other aspects. But the most important, in my opinion, reason is that in fact there is a lack of a simple alternative. ΛCDM is a fundamentally simple model. Not only it's simple, but also it's physically motivated. Because we know the cosmological constant can physically arise as a vacuum energy, which we know exists in field theory, because it's many times of vacuum different. One could imagine that in the context of anthropic density, even though even this small number could be realized in nature, we wouldn't be here, for example, if it was much bigger. So you have to take a plus in the equation. Also, there are too many tensions, at least 3, and there are even more. If you see our review, you will see there are even more tensions, but these are the most important ones. So it's not easy to make a coherent picture which will resolve all these seemingly not very related tensions. So let's compare with the previous standard model to see what happens in previous replacements of standard models. For example, the most obvious replacement is when we went from the steady state model, which was the standard model before the C1965, or the almost standard model, to much more symmetric model, to the Big Bang. And at that time, of course, there were two ingredients. One was that the data, this cosmic microvariable was found in 1965 by the Wilson Wilson. But also there was a simple alternative, which is the Big Bang model, which corresponds to the Friedmann equations. And so this was one of the reasons that it was very quickly the change was made. Similarly, from the previous standard model, which was the main, the so-called SCDF, which involved only matter, a flat universe including only matter and radiation, ΛCDM, where the data also about 25 years ago, the supernova data and other data, indicated the same, but there was also a simple alternative, the cosmological constant, which was simple and generic. Now, these are the people who pioneered this change from SCDM to ΛCDM even before the supernova data, and these are the data which gave the initial. These were tensions, much weaker tensions compared to what we have today. But because there was an alternative model, they actually were able to predict it early enough, even before the supernova data appeared, so it's an expansion. So the question is, what is the new simple replacement of ΛCDM that will remove tensions with just 1 or 2 generic parameters, simple and generic model? Now, in order to identify these degrees of freedom, one has to understand deeply the data. To understand what are the assumptions involved in each observation, and then try to understand and see what kind of assumptions could be violated in the context of a concise theoretical framework. Because we don't want to understand the data just to find systematics, because this is not theoretical, this is not interested so much in that. We want to understand the data because we want to see what theoretical model can actually address and change the assumptions made here. So that's why I will try to go a little bit deeper into data, from understanding of the data from this point on in the talk, to try to show you what could be the weak points, or the assumptions hidden in its measurement, so that one can actually then build models which actually violate one of these assumptions. Theoretical models. So, let's understand first of all how do we measure the Hubble constant locally, using local measurements, and one is what's called standard candles or standard rulers, which are objects whose luminosity and scale are known and can be used to measure distances, because to probe the Hubble constant and the h of z, we need to know redshifts, which are easy to measure, and second we want to know distances. And to measure distance, you need to have information to use some kind of probe which has known luminosity, and known size. Now, the most powerful standard candle that we have are the type 1a supernovae, which are powerful enough to be seen at cosmological distances, but also have more or less a luminosity, intrinsic luminosity, which can be understood and standardized using different other probes which are local. So here you see, for example, an observer away from a standard candle like a supernova, a Cepheids, or a gamma ray burst, which of course is not very good at a candle, it's just go very high in redshift. And imagine that you have a distance dl between the observer and the supernova, and imagine you measure the intensity, the apparent luminosity coming from this object, from this candle, and imagine that you know the absolute luminosity, the power emitted by this object. And so then there is this relation which shows that the apparent luminosity is equal to the absolute luminosity divided by the area of the sphere around it. And dl is in a Euclidean space with the absolute distance. Now, in a cosmological framework, dl is not exactly, depends also on the Hubble parameter, and this dependence is shown here. So dl of z is c times 1 plus z times dl 1 to z, dz prime h of z prime, where z is the redshift of the observed supernova. And you see here that if we measure many supernovae at very redshift z, we can make a plot of h of z, and thus probe the Hubble parameter using these standard candles. And we have two different domes. We have supernova, for example, and we have also gamma ray bursts, we have quasars, etc., which can be used in principle, but the most accurate one is supernova, which appear at redshift between 0 and about 2.5 to 2.6. Now, astronomers usually use, instead of apparent absolute luminosity, they use the apparent absolute magnitude here, which are connected by a logarithmic relation that we see here. So in what follows, I'm going to use this formula as opposed to this one, because that's what is used to make the fix in the data. Alternatively, one can use the angular diameter distance, which involves towards an object which has known scale, known size, and this could be, for example, the sound horizon of the cosmic microwave background. If we measure the angular scale with this sound horizon, with this standard ruler, we can infer the angular diameter distance, which depends again on the Hubble parameter. So we have this dA of z measured through the scale, and the actual scale, cohoming scale, and the theta angle, which is probed there. And if we measure dA of z at various redshifts, we have again information about the Hubble constant through a different type of measurement. So these measurements involve the baron acoustic oscillations and the CMB spectrum, where one can probe the sound horizon recombination. The baron acoustic oscillations probe redshifts up to 0.1, while the CMB spectrum plots the south horizon at its original scale, which is at redshift about 1,100. So the same thing is projected in this large structure here. That's why we can measure it also at because it induces fluctuations in the elastic structure, and these fluctuations are measured and through the barnacles oscillations. And we also probe the same phenomena both in this redshift and also in this lower redshift through the barnacles oscillations. So we can plot independently these Hubble parameters. And the key problem here is that the HOD that we obtain from this type of approach is shifted compared to the HOD that we obtain from this approach by a delta H of naught, and that's the basic problem. So, in order to measure now, to go to the simplest case, which is the local measurements of supernovae, one need to calibrate supernovae using other objects, which are standard rulers, standard candidates at lower redshift, at local distance, known as Cepheids stars. For these stars, we can measure their periodicity, their period of pulsation, because they have a period of changing of luminosity, and we can correlate this using geometric measurements to their actual absolute luminosity, construct this calibration curve, which connects the increasing property with the luminosity of these objects. And if these objects happen to be, after we calibrated, they happen to be the galaxy which also has supernovae, we can say that they have the same distance as the supernova, and then we can infer the luminosity of the supernova using this calibrator, which is called Cepheids. So the idea is to calibrate Cepheids stars locally using parallax methods, and then use them to calibrate supernova at higher redshifts, use them for a cosmological argument. So here a pictorial issue of this distance ladder method. First, we use parallax methods to measure the distance to Cepheids locally within our galaxy or neighboring galaxies. Then we see the same Cepheids in other galaxies which also have supernova hosts in them, which are up to about 30 megaparsecs, which are still not in the Hubble flow. There you cannot make cosmology, where you can calibrate supernova in the galaxy. And once we calibrate supernova using Cepheids in these distances, then we go beyond 30 or 40 megaparsecs, we go to 150 megaparsecs, where only supernovae can be seen, and not Cepheids, which are not so as powerful. And then we construct the Hubble diagram and measure the Hubble coordinates. These are the so-called three ranks of the distance ladder. One is geometric calibration of Cepheids, then is calibration of supernova using Cepheids, and finally, use of supernova to find H0. These are the three ranks of the distance ladder. So, once this is done, one has the measurement, this is the calibrated Cepheids stars to calibrate supernova in the galaxy, and then we use calibrated supernova at distant star galaxies to find H0 and H of Z. These are the three ranks. So, another calibrator is the Cepheids, is the so-called tip of red giant calibrator, which involves red giant stars, which are at this tip of the HR diagram. These are the brightest essentially stars, red giant stars in the HR diagram. These are bright red giant stars that have nearly exhausted their hydrogen, and they experience a sudden flash of helium burning. So these have more or less the same luminosity. They can be calibrated to also calibrated supernova. So instead of Cepheids, one can use red giant stars. And so, assuming that then we have measured somehow this way the absolute magnitude of supernovae, how can we measure H of Z in some detail? So the question is can we fit type 1a supernovae in order to find the Hubble parameter. This one uses this relation here, which connects the apparent magnitude with the absolute magnitude of supernovae, and with the luminosity. This is actually the relation that I showed in the previous luminosity. This is the magnitude. And one defines the so-called Hubble free luminosity distance, which doesn't involve H0, and they rewrite this equation as an equation between the apparent magnitude, the absolute magnitude, the Hubble free luminosity distance, and the Hubble parameter here. And you see by measuring this part here, we can measure, in fitting this luminosity, this luminosity, we can measure this combination M plus H0, which is degenerate. Unless we measure M separately, we cannot measure H0 because you see this one parameter, which is a constant parameter, and involves both of them. And this parameter I call it here calligraphic M. This is this combination which can be measured in the Hubble law. So if you go to the Hubble law and you have this luminosity distance, then you can only measure this combination. So the idea is to measure this, and then to break this degeneracy, you have to measure separately, locally, the absolute magnitude using Cepheids. If you don't measure the luminosity supernova locally using Cepheids, then you can never isolate H0 and measure. So the idea is to measure it locally at up to 40 megapascal using Cepheids, and then fit with kinematic expansion for low z this luminosity distance here, and then fit this, assuming, of course, that the value obtained for L here for low redshift, for very low distances, is the same as the value of L in the cosmological distance, that is at the redshift left larger than 0.01. Because we have the low stars at the redshift 0.01, at lower redshift, we have very big peculiar velocities of galaxies, so we cannot measure the Hubble constant. We have to go to higher distances, where the redshift is big, and then you can actually see the Hubble law. Otherwise, you just see peculiar velocities of galaxies locally. So it's important to go to higher redshift, but you can only calibrate for low distances, where N can be measured. So you calibrate here, locally for the low Hubble law, and you assume that this N is the same when you go out in the Hubble law, where the Hubble law exists. That's a big assumption. And we know that there is a degeneracy between N and H0, but we also have to assume that there is. Now one can also go to the Hubble law afterwards and very high redshift, at me up to redshift equal to 2, because this involves redshift up to 0.1 here, between 0.01 and 0.1. But if you go to even higher distances, higher redshift, up to Z max equal to 2, you can also do the same thing, parameterize H of Z using this equation, which leads to a luminosity distance coming from this opening not of the Hubble, of the cosmographic study, you parameterize using the cosmological model, and then you measure the parameters of the cosmological model, omega zero matter, and this calligraphic M or other parameters you can have in your cosmological model. So these are the rules of the game. You measure Hubble constant up to 0.1, then you go to larger than 0.1, you measure whatever parameters of your cosmological model. That's by fitting, by minimizing this chi-square here, which involves this cosmological parameter. These are the rules of the game, and this is how people do it, and have been doing it during the last more than 20 years. But during the last 5 years, they have been measuring this H of not in very big accuracy also, and found that as this value. So alternatively, you can measure H0 using different kinds of approaches, like time delays. You can use, for example, gravitational lensing, from lensing, which will have the measure this angles here of the lens, and this is the equation background. But images which have, for example, time delay between the signals, and using this time delay, one can measure the Hubble constant from this equation here, which connects these measured angles. This is the difference among various images for these angles. And this is the redshift of the lens, which can be measured, this galaxy here. And using these angular diameter distances, one can, assuming that modeling this potential also, one can actually measure H0 using this time delay from gravitational lensing. That's another method which is independent of the distance value. So that's an important method because it doesn't assume any calibration by Cepheids locally. Alternatively, one can also use gravitational waves to measure again H0 by using coalescent microbinaries, which we can measure both their distance using the gravitational waveform. And if one happens to also know the electromagnetic redshift, using the electromagnetic counterpart, we can use this equation here, which shows that the amplitude of the gravitational wave is inversely proportional to the distance, not distance. And this is the chipped mass for these two masses, and this is the frequency of the gravitational wave. And by measuring the chipped mass and the frequency of the gravitational wave, this is measured by the derivative of the frequency, which is chipped mass, which is the mass. It depends on the mass of the coalescent of the stars. We can have a measurement of the Hubble constant, which is not accurate at all at this point. You see here this standard side measurement, which, however, goes somewhere between the two measurements of the Hubble parameter. but of course cannot really be used to decide which one of the two is correct. So this is another independent measurement, which in the future will perhaps give us an idea of which of the two is the correct measurement. Now, as I said previously, the second way to probe the Hubble parameter is using the standard ruler, we say the sound horizon, and we start by measuring this angle to the sound horizon, and which can be measured. Then we, using either the CMD angular power spectrum or using the Barnard oscillations in the matter power spectrum, which you see here. So this is measured, we raise either 1100 or lower it using this spectrum. This scale of sound horizon can be calculated, assuming that in fact assuming that the expansion before the decoupling is given by this formula where h of a depends on the baryon matter, the photon density, and the CDM density, and these are inferred all of them by this power spectrum, and also by equivalency. So you put standard expansion before decoupling, before the CMD photons were released. Then you use this relation which connects this angle with the sound horizon scale and the co-moving angular diameter distance. And you put in the value of RS, you calculate, you put in the co-moving value of the DAOC, which can be obtained with this parameter in the process of standard model. So this can be obtained from the standard model parameters, this is TOC, and you see this DA and H not in the numerator here, which was here in the denominator, went up here. So by measuring this, we can and the sound horizon and using this parameter, the standard model of magnetic matter, we infer the value of H naught this way. So this is the measurement, it has some assumption here, the sound horizon and the expansion from present to the present Z. And of course the expansion from the Big Bang or after the inflation actually to the time of decoupling, which are the RS. So if we impose the standard model predictions for these quantities, we infer H naught. And the H naught is inferred to be, as I said before, about 67 kilometers per second. Now this sound horizon here, one can say some more things about it and say that why is this important? Because why is it depicted into the CMB power spectrum? Before recombination, we had plasma coupled to photons, so it's like we had some expanding spherical waves driven by the pressure of the photons on the baryons, and this induced some baryon perturbations driven by formal pressure. But at recombination, the photons do have neutral atoms forming, the photons free stream away. These spherical waves freeze, they stop expanding at this particular time when the horizon, the sound horizon was present. And so we can see in the universe spherical cells of baryons which emerge from this old time of freezing when the cells froze from expanding. And this is a typical scale, therefore we can measure the scale either in the CMB or in the large scale structure. And here you see exactly the phenomenon that I described. You see here that, okay, I'll just show you here. So you see here this expanding, these are photons and gas, and at some point the photons decouple, they go away alone, and this density peak freezes there. And later on, dark matter, which is this black one, follows and clusters, and these is transmitted to the dark matter of galaxies. And the same thing as we saw here in this picture, you see the expanding waves. They expand, they freeze at some point because the photons stream away alone. And this freezing cells of baryons remain there, and they start accreting matter on these scales. You see many such horizons, superposed. So we have these scales, and then later on matter accretes on them, and so this scale is depicted in the power spectrum of large scale fluctuations. And you see as galaxies form, there is they tend to form along this scale. You see this deformation. So the scale is depicted now in the distribution of galaxies, in the correlation function of galaxies. And therefore can be measured by measuring the correlation function of galaxies, that's what we learned in the power spectrum. And you see here pictorially how we can actually see the scale in the galaxy correlation function, which is shown here how many galaxies have a particular separation. You see there are more galaxies which have a separation corresponding to this characteristic sound horizon scale, so we can measure the scale through this correlation function effectively. This is the frequency of distances separation. And you see there are two peaks, this one, this is the peak that we expect to have from large scale sound, and then there is additional this peak which is coming from this characteristic scale of the sound horizon, which is built in the large scale structure. So it's built in both in the CMB power spectrum, because we probe exactly the typical scales at the time of recombination, but it's also depicted here in the baryon acoustic oscillation through this particular separation peak. That's why this scale is a very important, well understood scale, because see, in deriving this, of course, we have to make some assumptions about the background cosmological model. So if you assume ΛCDM, then you get this kind of picture of this. Now, in the determination of H0, we have to use the luminosity of supernova, using the local measurements, of course. Okay? Now, because it's the difference between M and H0. Now, if we assume that the measurement of H0 from the CMB, from the sun horizon scale, is correct, and we assume that this H0 obtained from the CMB here is correct, we can use this to calibrate supernova. Instead of calibrating them using Cepheids locally, we can say that the correct distance will be given by the CMB as obtained from the calibration of the sun horizon evolved up to date. So you can assume that this Hubble parameter is correct, and go into this degenerate combination as I showed before, and instead of measuring M and deriving H0, you can put in H0 from the CMB and derive M, the luminosity of the supernova, as obtained from the CMB. You can, of course, use this value for this calligraphic M, and this way you find that the absolute magnitude of supernovae as obtained to be consistent with the CMB measurement of H0 is minus 19.4, plus or minus 0.027. And this is inconsistent with the luminosity coming from the Cepheids. This is smaller by about 5 sigma compared to the absolute magnitude you see for supernova from the Cepheid star. So deeply into this Hubble tension is hidden inconsistency in the absolute magnitude of supernova between the magnitude you deduce from the Hubble flow and the CMB coming from above, and the magnitude you deduce from the Cepheids coming from below, from low distance to high distance. So this inconsistency is known also as M tension, which is equivalent to the Hubble tension, and deeply rooted in this tension is also the Hubble tension, because as I said before, in the context of the Hubble tension, one measures calligraphic in the Hubble flow. One also measures using Cepheids or other calibrators the corresponding M at lower exits from Z less than 0.01, and then uses this parameter which is measured directly in the Hubble flow, assuming M is the same at low and high exits, and then if one uses this M here, from this Cepheids, one deduces the Hubble tension from the supernova, which is larger than the Hubble parameter from the CMB. So this is the basic idea that we have here. So on the other hand, local measures that you see here can measure H, local measures which are not dependent on distance ladder, have an H which is consistent more or less with the CMB, apart from these two which are from less than time delays and from the recombination, which are actually there's some disagreement, a lot of systematics, that is not a very accurate measurement. On the other hand, from distance ladder, you find these kinds of measurements which are all consistent with the values by laser diffuse measurement to give this larger value. So the question is that whatever is the problem here may be hiding inside this distance ladder procedure. So could we be missing something with all local calibrators? Could there be a change between local calibrator scales and Hubble for scales? Is the question about this. So this brings me to the one possible hypothesis one can actually make, which is that the supernova luminosity may change, in fact, physically, between the measurements of Cepheids here, less than 0.01, and the measurements obtained from the interstice of ladder approach. And these are the supernova actual magnitudes obtained assuming the Hubble parameter from the CMB. And you see, since the Cepheid measurement coming from here and this is coming from the Hubble flow, the only way to make these two consistent is to assume that there's a transition, a change of n due to some gravitational effect at this value about Z0.01, and this is the M transition hypothesis, which would be a fundamental physics question induced on the actual magnitude at about Z0.01, where the would be the only place where these two can be made consistent. So potentially this can also solve the growth tension, because if it gives a gravitational effect, this could actually also reduce gravity at every time compared to what we know now, and would weaken the growth fluctuations. So anyway, so these are the basic ingredients of various classes of models which we have right now. So I will have to you see that the possibility of bringing this down by using this transition, bringing this up using the sound horizon, using a change of the sound horizon due to some physical process at every times, and also one can also deform the Hubble parameter like this, so that it matches the value of Hubble constant at times. Now this, of course, is a problem because there are various issues with these models. The most important problem is that if you try to deform this Hubble parameter, here, this Hubble function, you get in trouble with the Barnard oscillation by times with supernova. So this class of models have been put into disfavor. The most important models are these ones right now. The most one actually this one could change the sound horizon by some early dark energy, for example, to change the sound horizon, reduce the sound horizon, and therefore increase the Hubble parameter. And also the possibility of some local physics change which will change the actual magnitude supernova. Now these are some papers which discuss. So an abrupt transition event may be ready to resolve this tension, either coming at early times before recombination, where it will change the sound horizon, or at late times where it will change the actual magnitude supernova. So this would be probably a gravitational transition. I don't have much time to say much about that, so I will just skip this part. So it would involve some kind of change of gravity and this kind of redshift, which would induce by 10% addition of G effective at this scale. This would change the actual magnitude supernova. It would also possibly fix the growth tension by increasing gravity. You see here, by lower value of G effective, one would have this change of scale of smaller growth. And so the main question is, would there be such a hint in the data? Would it be consistent with data? And the answer is, in fact, it can be consistent because the data mostly shows the derivative of the gravitational constant and not so much its magnitude, so it reasonably can be consistent. Are there hints of this? In fact, we have some papers where we show some hints of this in other data, like universal data, and some other people also found such kinds of hints of change of physics at about Z0.01. And also, is there a mechanism to induce this? And in fact, one can consider like, this is the hint that I said before, if this is the Cepheid, the magnitude supernova measured by Cepheid without allowing this transition from the source data. But if you allow this transition, you find that the two higher costs of Cepheids seem to have a reduced absolute magnitude at the redshift of 0.01. And this is an analysis we have done recently. A theoretical model which can induce us is a scalar tensor theory, where one allows the evolution of the effective strength of gravity. Lagrangian like this one, for example. And in this case, what we have a transition from the force vacuum to the true vacuum. This would also induce anisotropy on scales of about maybe 40 or 50 megaparsecs. And so it would be some bubbles of gravitational field being gravitational being different in this bubble. So if we were in this bubble, we would see close to us a different value of absolute magnitude supernova compared to outside of this bubble where the gravity would be different, we would have different kind of strength of gravity. Or alternatively, you can imagine instead of having this special transition or a time transition like we suggested, where there is a feature in f of I, so as phi grows according to scalar potential, one would change suddenly the gravitational constant at some particular time to induce this kind of change. So anyway, these are some qualitative theoretical thoughts which would induce this kind of models. So this will be, and this will bring to the end of my talk. These are the main points which I wanted to say. First of all, the standard model is a simple and successful model consistent with wide range of observations. A few tensions of the model parameters indicate the possible presence of new physics. There are three main classes of model that I would try to replace ΛCDM, which involves either a local transition or a change of the sound horizon or a deformation of HG, but as I said, this last one is not really popular today because it has problems with data. And an abrupt change of physical law during the past 150 years, could potentially have interesting implications for this tension. Thank you for your attention.
Thank you very much for a very interesting talk, and it's time for questions.
The calculation of Cepheids is about 1%. And you presented data concerning the calibration of supernovae 1A, which you got the same model, maybe even better. How is that possible if we know that there are about maybe 1 dozen or 2 dozens of supernovae 1A that can be calibrated?
Okay, first of all, what I'm saying here is not that there is something wrong with the Cepheids. I mean, they're saying that the Cepheids were very nicely calibrated, there's no problem with that.
No, what I'm saying is there's problem, perhaps there's something wrong with the calibration of supernovae 1A.
Okay, that's a possibility. I'm not saying that this is not a possibility, but in the context, I mean, these things have been tested very well by the experimental, by the observations, and they have tested various types of systematics, and so far they haven't found any fit to systematics. So there's a big debate, it's lasted for a long time, but even though everything has been tested, it looks like, in terms of systematics, this measurement seems to be robust. I'm not an expert in this part, so I'm not going to say more, but I'm just saying that the observers, the SUS team, claims, and the other team, not only that, because the other team who use distance learning approach, claim that the issue of systematics seems to be okay. So this measurement 1% appears to be good. But what they cannot really say, and they cannot prove, is that what they calibrated using irredshift less than 0.01, where the Cepheids and supernova coexist, is the same as or redshift larger than 0.01, where supernova alone are used to measure the. So if there was a transition, as we seem to find in some analysis that we made, at this particular point, no one would be wrong. Everybody would be correct. I mean, both the observers and the CFD also would be correct, because in this way, this natural change of gravity would induce this kind of phenomenon. So these are telling there's a blind spot there, which has not yet probed. In fact, we tried to probe this analysis as before. We tried to do here the analysis of the SUS. And so we said, okay, what they do here is what they do in this part is they assume here that the MD, the magnitude supernova, is the same over this whole range of redshifts where they have Cepheids and supernova. These are the hosts, the galaxy hosts. This is the absolute magnitude for galaxy hosts where they have both Cepheids and supernova. What we did, we did this analysis, we saw, of course, we understood this analysis, we reproduced the results, and then we said, okay, imagine that at some distance here, there's a different MD. Reanalyze the same data with this assumption. And then you see that if you allow this, these two hosts, the highest distance hosts, spontaneously go down and seem to match the supernova calibrated from the CMB. Because these two hosts have no information about the CMB here, it's just local physics. These supernovae are calibrated from the CMB, from the south horizon. Okay, here. But how could these 2 points here drop down exactly when the supernova from the CMB wanted it to be? So this is a puzzling issue, and we'll talk to the SUSD. We have a lot of that, and this issue to improve data here, put more Cepheids, perhaps, or supernova, to see what we find here, which has big error bars, of course, cannot be faster. But if you reduce this error bars, then you would actually see the thing happening within the Cepheids. If they had more data there, and the problem is, of course, there are not so many supernovae appearing every year in these galaxies because every supernova in this distance is very rare event. But it's about 1 supernova a year, but they would put more Cepheids there and see what's the reduced error bars in this area.
One possibility is, because you mentioned already all these cosmic dipoles, one possibility is to generalize the redshift utilization for some inhomogeneous or anechoic models where you have extra degrees of freedom. Is it still possible? Because we know that it's hard to fit with all the data. But is it seriously considered now? And your scalar tensor approach, is it just kind of spatially inhomogeneous or anisotropic?
Okay, let me start with the second part. Here you see that there are 2 ways to reduce this gravitational transition. One is to use a force vacuum decay, which in that case it would be a special event. So you would be in a offset in some body, so in that case we would have naturally some kind of anisotropy where a much smaller scale is observed, so in principle it would not be directly related to what's observed in the large scales, but we would see an anisotropy there. So this part predicts an anisotropy, or the second approach is to use a quintessence type, scatters a quintessence approach, where you have no anisotropy, but you have a feature in this non-minimal coupling function f of phi. If you have an discontinuity there, for some reason, along with a quintessence, smoothly moving quintessence field, then you could naturally induce this shift of gravitational constant at this particular resonance is required. Now, in terms of inhomogeneous models, of course, okay, most of them are not really, it's not easy to use them to address the Hubble constant, and in principle it's possible. One would have to somehow devise a different kind of approach. We are having some inhomogeneity in the Hubble parameters, which have been observed, but it's not really a simple way to proceed. There are no models which address simultaneously the dipole tension with the Hubble tension. That's an issue which needs some consideration, but it's not clear.
Isn't this jump of f of phi and ad hoc assumption? Or
it's not ad hoc. Well, it doesn't have to be any discontinuity, any jump of f of phi, which exists in this is any abrupt change of f of phi. Of course, here I saw it in a very simplistic way. But even in a f of phi, which is very smoothly changing in the orbit is constant, if you superpose there some feature, some glitch of any type, would naturally induce a change, a shift of G vector. So the key point there is that with this function, you are not in conflict with any observation. For example, in this low redshift region here, CF of phi is constant, so there's no problem with solar system tests or whatever. Also, before that, it's also constant. In fact, the time derivative doesn't change because there are very big constraints on the time derivative of G, of f of phi. So you need something like that to go through the filters of cosmological constraints, gravitational constraints. But this actually can escape. I mean, you have a feature there. It's something that wouldn't be measured easily, up to about 5 to 10%, of course. You can go 50% because then you have nucleosynthesis bounds which allow you to go up to 5 to 10%. But such a glitch is allowed. Sometimes there's nothing that can prohibit that. So thank you very much.